Hello and welcome back to A Slice of Physics. We're now ready to talk about Newton's law of gravity. This law tells us about the forces between two masses, so we will learn what that force is all about, and we'll build on that with a discussion of the generalization of acceleration due to gravity. And we'll take the example of the Earth and the Moon and figure out the force between these two objects. And in doing that, we'll also discuss what causes tides in our oceans. By now we have spent a lot of time working with this lowercase g, which was the acceleration due to gravity at or near the surface of the Earth. And the value of that was 9.80 meters per second squared. And now it's time for us to understand more about this. Where does this acceleration come from, and where does this value come from? Newton explained all of this in his general law of gravity. What Newton found was that any two masses will have an attractive force on each other. So masses are like magnets, if you will, but the difference is that magnets can either attract or repel based on which pole is facing which pole, whereas masses only have attractive forces. So if I have a mass here that's m1 and another mass here that's m2, and let's say they are separated by a distance of r between their centers, then it turns out that the mass 1 will have an attractive force on mass 2. I'm showing it a little offset from the object so you can see it. So this is force of object 1 on 2. And in return, m2 also has a force on m1, which is also attractive. Both masses attract each other. So let's call this F2 on 1. The magnitude of these forces is given by Newton's law of gravity, the equation that he came up with, and that simply says F1 on 2 equals F2 on 1 in terms of magnitude, and that's given by this equation, capital G, m1, the mass of the first object, times m2, the mass of the second object, divided by the square of the distance between them. So you know what m1 is, m2 is, and r is, but this g is a new term. So let's define that. That is Newton's gravitational constant, and that has a value of 6.67 times 10 to the negative 11 in SI units, and its SI units are Newton meter squared over kilogram squared. So pretty complicated unit for a constant, but you can see that when I use that unit over here and multiply by the two masses, the kilogram squared will cancel, and divide by square of the distance, the meter squared would cancel, and so I would be left with just Newton, which is the unit of force. This guy, capital G here, is a universal constant. It's the same everywhere. Whereas the lowercase g value of 9.80 that we've been working with so far is only true on or near the surface of the Earth. It's not true everywhere. So we get the magnitude of the force between masses from that equation, and we get the direction using the fact that it's always an attractive force between masses. And by the way, if you are thinking that because these two forces are equal in magnitude and opposite in direction, do they form a third law pair? That's a good thought, and you would be correct. These two do form Newton's third law pair, so they will always be equal in magnitude and opposite in direction. This might initially be surprising for some of you. If mass 1 is a lot bigger than mass 2, how come they both exert the same force on each other? A practical way of thinking about that is, as you're standing here on the surface of the Earth, you certainly feel that force, and you think the Earth is applying a force on you, an attractive force on you, which is correct, but it's also true that you are applying the exact same magnitude of attractive force on the Earth. F1 on 2 always equals F2 on 1. The reason you feel it a lot more than the Earth is because your mass is a lot less than the Earth's mass, so your acceleration because of that same force would be a lot higher than the Earth's acceleration because of that force. So let's continue to work with this equation to see what that means. So if I've got the force of gravity as G m1 m2 over r squared, and let's say this is, I'm taking the F1 on 2. So I'm looking at what is the force on this mass 2 from mass 1. And you know I can write force always as mass times acceleration. In this case, the mass in question would be m2 because I'm taking the force on 2. So just using this right-hand part of this equation, I can see that I can divide both sides by m2, and the m2's would cancel, and that would give me acceleration due to gravity. This is a gravitational force, so let's call this acceleration due to gravity, equals g m1 over r squared. So the acceleration due to gravity that mass 2 would feel would be the universal constant times the mass of the other object that's responsible for the force divided by the square of the distance between them. And if we take the very special case of the Earth over here and you standing on its surface, and we try to figure out what the acceleration due to gravity would be on the surface of the Earth, you would have to use the universal constant over here. You'd have to use the mass of the Earth, and the mass of the Earth is 6.0 times 10 to the 24 kilograms. And the distance is from the center of the Earth to you is the radius of the Earth, and the radius of the Earth is 6.4 times 10 to the 6 meters. And if you use these specific values in this equation, you would get the acceleration due to gravity, which we call just simply lowercase g, on this specific case on the surface of the Earth as 9.80 meters per second squared. I'll leave the calculation part to you to verify that that is the case. Okay, let's move on to the example that we wanted to take. Let's say here's the Earth and here's the Moon. So like I just said a few minutes ago, the mass of the Earth is 6.0 times 10 to the 24 kilograms. The mass of the Moon is 7.3 times 10 to the 22 kilograms, smaller by a couple of magnitudes than the mass of the Earth. And the distance between the centers of the Earth and the Moon is 3.8 times 10 to the 8 meters. That's about 380,000 kilometers, or more than 200,000 miles. So if we want to find out what the force of Earth on the Moon is, we can use the equation that we just discussed. So it'll be g times mass of the Earth times mass of the Moon over square of the distance between the Moon and the Earth. We know all of these values, and if you do that calculation, you will get a pretty large force. You would get something like 2.0 times 10 to the 20 Newton. That's the force that's responsible for keeping the Moon in orbit around the Earth. And as we discussed before, the magnitude of that force is also equal to the force of the Moon on the Earth. And by the way, this force of the Moon on the Earth, or rather the difference in that force on the near side of the Earth versus the far side of the Earth, is what causes tides. You see that this force is dependent on r squared, square of the distance, so it's quite sensitive to the distance. So the force that the Moon applies, let's say the Earth is back here, the Moon is here, the force that the Moon applies on the ocean that's nearer to the Moon is larger than the force that the Moon applies on the solid part of the Earth, and that's larger still than the force that the Moon applies on the far side of the ocean. And the result of that is that the ocean bulges in this very exaggerated picture on the part of the Earth that's facing the Moon and the part of the Earth that's opposite the Moon. So you will have a high tide whenever the Moon is overhead or right below your feet. Now the Sun is also responsible for tides, but it turns out that even though the Sun's gravitational force is higher at Earth than the Moon's, the difference across the surface of the Earth, Moon dominates that calculation, so the tides are governed more by the Moon than by the Sun. Now let's discuss the general form of acceleration due to gravity. So if we want to talk about what is the acceleration due to gravity from the Earth, not at its surface, but at the Moon's position, then we would use this equation and divide it by the mass of the Moon, just like we did here. Acceleration was just simply the force divided by the mass of the object that was feeling the force. So this would simply be g times mass of the Earth divided by square of the distance between the Earth and that position where the Moon is. And when you do that calculation, you would get an answer of 2.8 times 10 to the negative 3 meters per second squared. So like you verified over here, the acceleration due to gravity on the surface of the Earth was 9.80 meters per second squared. But if you keep everything else same and just say, I'm not on the surface of the Earth, I'm near where the moon is, then the acceleration due to gravity will be a much smaller number because of its dependence on the distance. So in this slice of physics, we learned all about Newton's law of gravity. We saw that it's an attractive force between any two masses, and it's given by this equation, where it's proportional to the product of the two masses and inversely proportional to the square of the distance between them. And this gravitational constant is a universal constant which has this value. We also saw that the general form of acceleration due to gravity from any mass m1 at any distance r from it is given by this equation over here. And we calculated the force between the Earth and the Moon and discussed the reason for the tides.